In lab number 7, we're going to discuss configuring route redistribution. We will begin by discussing the need for route redistribution and explain the function of a boundary router, of a seed metric, and we're going to see the syntax for setting up a route redistribution. Then what we're going to do out in our topology, we're going to configure a portion of it for EIGRP and another portion of it for OSPF. Then we're going to mutually redistribute routes between those two different routing protocols, and we're going to verify that route redistribution did occur as expected.
In this lab, we're going to discuss redistributing routes from one routing protocol into another routing protocol. In fact, we're going to do something called mutual redistribution, where we redistribute routes between EIGRP and OSPF mutually between one another. First of all, let's make sure we understand the need for route redistribution. Let's say that we're transitioning maybe to a more advanced routing protocol. Let's say that we had been using RIP version 1 as an example, and we're transitioning to OSPF. Well, it might not be an overnight upgrade, a forklift upgrade, if you will. So what we might do, we might run a portion of the network using the old routing protocol and a portion of the network using the new routing protocol for a period of time and migrate from one routing protocol to the other. During that transition, where we have both routing protocols active, we need to do some redistribution so that all of the routers in the topology, regardless of which routing protocol they happen to be running, have full reachability throughout the network. Another reason we might need to redistribute a routing protocol is we have a couple of companies that merge. One company was running OSPF as an example, and another company was running EIGRP, and maybe those networks are under different administrative control and they really don't have any need or desire to consolidate and use a single routing protocol. We might have to ongoingly have these two different routing protocols running in our network. In that case, route redistribution becomes very essential to communicate the route information throughout the far reaches of the network. And even without the merger of companies, sometimes within a company, different areas are under different administrative control, and one area might have a special need for a specific routing protocol. Well, we might need to have that routing protocol interoperate with a different area of administrative control within the company. And when we talk about tying these two different routing protocol domains together, the router that sits in the middle is referred to as a boundary router. The boundary router is going to connect, in our case, to an EIGRP network as well as an OSPF network. And this boundary router is going to be able to redistribute routes from one routing protocol into the other. And like we said, in this lab, we're going to be redistributing OSPF into EIGRP and EIGRP into OSPF, but realize this boundary router, it could redistribute statically configured routes, directly connected routes, or routes learned, as we'll see in this lab, via a different routing protocol. Consider the topology on screen. We have 3 routers. One portion of the network is running RIP, one portion of the network is running EIGRP, and notice R2 has an interface in each of these different routing protocol domains. Router R2, therefore, becomes our boundary router. And it's going to be router R2 that we need to configure for this redistribution. One challenge we might have, though, as we're redistributing one routing protocol into another routing protocol, is that the routing protocols often use different metrics, different measurements of a route's attractiveness. Therefore, when we're redistributing a route from one routing protocol into another routing protocol, we might need to configure a seed metric, also called a default metric. This will give us a relative level of reachability between dissimilar routing protocols. Consider, for example, on screen we have an area of the network running RIP and an area of the network running EIGRP. And as we learned earlier in these Video Mentor labs, RIP uses a metric of hop count, and EIGRP, according to some of the literature, has a metric composed of elements such as bandwidth, delay, reliability, load, and the maximum transmission unit size. So what we can do is, in the boundary router, we can define a seed metric. And this seed metric can assign, in this case, a hop count to routes coming from EIGRP into RIP, and it could assign a default EIGRP metric for routes coming from RIP and going into EIGRP. And there are 3 main ways that we can define this default metric or the seed metric. One is to use the default metric command. In fact, we will see that command used in this lab. Another approach is to use the metric parameter in the redistribute command. And a more advanced option is to use a route map configuration. However, in this lab, we're going to be redistributing between EIGRP and OSPF has a default seed metric of 20. So routes coming from EIGRP, they're going to inherit a default metric of 20 as those routes are injected into OSPF. So we don't really have to configure a default or a seed metric for OSPF. We are, however, going to configure a default metric for EIGRP to assign routes coming from OSPF and going into EIGRP. Let's take a look at the topology that we're going to be working with. In this lab, notice that R1 is going to be functioning as our boundary router. First, we will go through all of the routers and we will configure them for the appropriate routing protocols. We'll configure R2 for EIGRP, we'll configure BB1 and BB2 for OSPF, and R1 will be configured for both routing protocols. However, just configuring everyone for these routing protocols is not going to give full reachability throughout the network. We're going to have to go to R1 and then perform some route redistribution to inject the EIGRP routes into OSPF and vice versa. Let's see the syntax that we're going to be using to accomplish that. First, we go into OSPF configuration mode as we've done in previous labs, and we can use the command redistribute EIGRP followed by the EIGRP autonomous system number, and we're going to give the keyword of subnets. Giving the keyword of subnets allows us to advertise specific subnets as opposed to a classful route coming from EIGRP, and that's what we will want to do. Then we will go into EIGRP router configuration mode, and we will redistribute a specific OSPF process ID, and then we will specify a default metric to be used, to be assigned to these routes coming from OSPF and coming into EIGRP. And we'll do that using these commands that we see on screen. Now that we've talked about the theory, let's go ahead and set this up. Let's begin our configuration on router R2. Router R2, you see, resides entirely inside of the EIGRP routing domain. Let's go into global configuration mode and configure R2 to run EIGRP. We say router, EIGRP, we give an autonomous system number of 100, and we're going to give a series of network commands. Remember, the network commands are used to specify classful network addresses for EIGRP. We say network 2.0.0.0 for the classful IP address of our loopback interface. We say network 10.0.0.0 for our fast Ethernet 0/1 interface. And finally, network 192.168.1.0 for fast Ethernet 0/0. Now, we follow this up with a no auto-summary command so that we're going to be advertising subnet information as part of our routing advertisements. Even though we configured the networks at their classful boundary, we're going to be advertising them using their subnet information. I think we're done with our configuration on router R2. Let's move over to router R1. And router R1 needs to be configured for EIGRP and also OSPF, you'll notice. First, let's say router, EIGRP, we give an autonomous system of 100, and we say network 192.168.1.0. We follow that up with the no auto-summary command. And now let's configure R1 for OSPF. Let's go back into global configuration mode, say router, OSPF, and we'll give a locally significant process ID of 1, and we'll say network 1.1.1.1, and we give a wildcard mask of 0.0.0.0 because the subnet mask was a 32-bit subnet mask, so the corresponding wildcard mask would be all zeros. And you'll notice for this OSPF network space, everybody's participating in area 0. So we'll say area 0. Next, we'll say network 172.16.1.0. This is for the network interconnecting R1 with BB1. And we give a 30-bit wildcard mask, which would be 0.0.0.3 in area 0. And for the network interconnecting R1 with BB2, we say network 172.16.2.0 with a wildcard mask of 0.0.0.3 again, area 0. And we're done with our configuration at this point on router R1. Next, let's move over to BB1. On router BB1, we configure it for OSPF. We say router, OSPF. We give a locally significant process ID of 1. And we say network 3.3.3.3, 0.0.0.0 for the loopback interface. This is participating, as everything is, in area 0. We say network 10.1.1.0, 0.0.0.3 in area 0. This is for the network interconnecting our backbone routers, BB1 and BB2. And one more to go, we say network 172.16.1.0, 0.0.0.3, area 0. This is connecting BB1 back to R1. We're done with our configuration on BB1, so let's move over to BB2. We give a very similar configuration on BB2, router OSPF 1, and we give a network statement first of all for our loopback interface, 4.4.4.4, 0.0.0.0, area 0. We say network 10.1.1.0, 0.0.0.3 in area 0. And finally, network 172.16.2.0, 0.0.0.3, area 0. This is the network connecting BB2 back to R1. We've now configured each of our networks to participate in one of two routing protocols in this topology. I wonder what the reachability is at this point, though. To check this, let's go over to router R2, which is entirely in the EIGRP routing domain. And from the perspective of router R2, let's do a show IP route. What routes does it know about? Interesting. The only routes it knows about are connected routes. It hasn't learned anything via any routing protocol. The reason is R1 only has one interface participating in EIGRP, and it's the same network that's connected to router R2. So there was nothing to advertise to router R2. What we need to do now is go over to router R1 and configure mutual route redistribution. In other words, we want to tell R1 to inject EIGRP learned routes into OSPF and to inject OSPF learned routes into EIGRP. Let's see how to do that. First, we get into global configuration mode, and we say router EIGRP 100, and we say redistribute OSPF 1. Redistribute OSPF 1, and with EIGRP, we do not have a default seed metric or a default metric that would be applied to any routes that we inject into EIGRP. Well, to be technically accurate, the default metric is infinity. So any routes we inject into EIGRP would be unreachable. So we need to come up with some way to say, when I inject an OSPF learned route into this EIGRP routing domain, I want it to have a certain metric. And what we can do is use the default metric command to specify components used to construct an EIGRP metric, such as bandwidth, delay, reliability, load, and MTU, as we discussed earlier. Let's specify those parameters now. Let's say 100,000 for our bandwidth, 10 for the delay, 255 for the reliability, 1 for the load, and 1500 for the MTU. Next, let's go into router configuration mode for OSPF, process ID 1, and we will say redistribute EIGRP Autonomous System 100 subnets. We use the subnets keyword to say when we're injecting these EIGRP routes into OSPF, we don't want to just inject the classful routes, we want to include subnet information. And notice for OSPF, I am not specifying a default metric. The reason is, OSPF, as we mentioned earlier, has a default seed metric. It's a default metric of 20. So routes injected into OSPF begin with a default metric of 20. And we'll just leave that. No need for us to configure a different default metric at this point. Well, I wonder if this configuration has now mutually redistributed EIGRP and OSPF routes into one another. Let's see if it has. Let's go back over to router R2, and reissue the command show IP route. And it looks like we have success. It looks like even though router R2 is only running EIGRP as a routing protocol, it has learned about routes originating in OSPF thanks to the redistribution we configured on router R1. Just to make sure that we have full reachability, let's ping the loopback interfaces of all of the routers in this topology. Let's do a ping to 1.1.1.1. Router R1. We'll do a ping to our local router 2.2.2.2. We do a ping to BB1 at 3.3.3.3. And finally, let's check the reachability over to BB2. Let's ping 4.4.4.4. And we have success. By just configuring the boundary router in this example, we were able to mutually redistribute EIGRP and OSPF routes. In this lab, we saw how we could redistribute routes from one routing protocol or one routing process into another routing protocol, and vice versa. That was called mutual route redistribution. And even though in this lab we were going between a couple of different routing protocols, remember we could redistribute between a connected route and a routing protocol, or a statically configured route and a routing protocol. And one of the big challenges we had was that different routing protocols oftentimes use different metrics, different measurements of how attractive a route is, and we needed some relative level of measure that we could use as we were doing this redistribution, and we talked about the need for a seed metric or default metric. We saw that OSPF had a default or a seed metric of 20 for routes being injected into OSPF, but EIGRP does not by default have a seed metric. So we configured a default metric for EIGRP, and we specified parameters that could be used in EIGRP's metric calculation. Parameters such as bandwidth, delay, reliability, load, and the MTU size. And those parameters could be inherited by routes coming from another routing protocol and being injected into EIGRP. And by doing this mutual route redistribution, at the end of this lab, we were able to have full reachability throughout the network. Coming up at our next lab, at lab number 8, we're going to take a look at a routing protocol that we've not yet discussed, Integrated ISIS, Integrated Intermediate System to Intermediate System Routing. This is a routing protocol that you might see used in a service provider environment. That's coming up next in Lab 8.